for the early screening of Alzheimer's disease. So, which has a high accuracy, affordable, non-invasive, and easy to use functions. Alzheimer's disease affects millions of people worldwide, with the cases expected to rise as populations age. Although two FDA-approved drugs has been available for mild case treatment, the current diagnostic methods such as PET scan and cerebrospinal analysis are invasive, costly, and unsuitable for early screening. According to the revised diagnostic guideline of 2023 of National Institute of Aging and Alzheimer's Association, blood-based biomarkers are recommended for clinical use for early prevention and diagnosis. There is one blood screen test approved by FDA in last May. However, how to detect the biomarkers is a challenge for the current technologies. Meanwhile, in AD drug development, to identify appropriate for the drug trial is time-consuming and costly. There is a need for the reliable blood-based predictive model for accelerating the clinical trial and reduce the cost. Many AD biomarkers with the concentration in blood actually don't need the conventional detection methods, making the accurate detection difficult. So, to address these issues, we offer a digital ELISA platform based on a microwave array, which providing high accuracy, sensitivity, and flex, and can be used for AI-driven risk stratifications. This microwave array actually is made of a PC with the dimension 1 inch times 3 inch, contains about 20,000 whales. Each whale with diameter of 10 micron. The PC plate actually can be produced by injection molding for mass production. Our digital ELISA is based on the digital detection. It's based on the digital detection of the single molecule in a microwave. Which is different from the bulk detection, analog detection in a bulk solution. The increased concentration of single molecule in the single whale and reduced noise enable it to be used for the low concentration of AD biomarker detection. This one is the digital ELISA workflow. First, we conjugate capture antibody on the magnetic bead and then mix with samples and detection antibodies. Those samples are loaded into the microwave and distributed into the microwave for reaction. After reaction, the microwave image was captured by digital ELISA reader which was made by ourselves. The captured image can be used to count the number of fluorescent and non-fluorescent waves. And based on the counting numbers, we can use the boson's distribution formula to count the biomarker concentration. Our digital ELISA reader is contained in size, which also has the automatic function to acquire both bifield and fluorescence image with a resolution of 2.5 micron per pixel. And the limit of detection fluorescence is down to 5 micrometer squares. This is the microwave image captured by the digital ELISA readers. The red spot actually is the non-fluorescent beads, and the green spot is the fluorescent beads in the wave. So we use the digital ELISA image analyzer that is also developed by ourselves. The grid of mask was loaded, array was loaded into the image, and to circle the microwave and counting the number of microwaves. So we can base on the number of fluorescent and non-fluorescent waves to get the average N9 per wave. In short, we call it AW. The AW actually was calculated from the ratio of fluorescent to non-fluorescent beads using the boson's distribution formula. The higher the AW value indicated the higher concentration of the biomarker. Here is one example of T-tau biomarkers measured by the digital ELISA. We can see that actually the AW increase is the concentration of T-tau. The linearity is from 3.125 to 50 picogram per milliliter, with R squared equal to 0.99. The quantity of bits used also influence the AW value, because the more quantity of bits, the more energy was captured, and the higher the AW value is. However, too many bits actually will reduce the energy and will reduce the captured energy per bit, which will also reduce the AW values. So in our case, for p-tau 217 detection, actually the optimal bit is about 80,000 running 800,000. The sensitivity also depends on the quantity of bits used. We can see that the sensitivity for 80,000 bits is higher than that for 800,000 bits. Meanwhile, the concentration of captured interbody will also influence the sensitivity of the digital ELISA. We can see that the more captured interbody, the higher the sensitivity. The repeatability of digital ELISA is effective, and also the limit of background, limit of detection, and the limit of quantity measured by digital ELISA for T-tau are 0.42, 1.5, and 1.5 picogram per milliliter. In conclusion, in comparison to the other commercial products, actually our digital ELISA offer a competitive price and cost effectiveness. Meanwhile, the common size of the system of the reader can be fit into any space constrained area, especially for clinics and pharmacies. The system is easy to deploy for scale applications and can be used for the card application. Thank you for your attention. Yeah, it is a good question. Why we use the magnetic bead? Because we want to separate the symbol into the single wire. So in everywhere, only one bit is allocated. So in that case, actually we can increase the concentration of the energy in one bit and also decrease the noise compared to the bulk solution resource. Okay, thank you very much. Okay.
Questions? I'm not familiar with this field, but can these be easily tracked on the microwave? It is easy to track the beads or orbits onto the hole. It's easy?
Actually, it's not easy to allocate and to distribute every magnetic bit into the microwave. So we use the microfluid channels to throw the channels into the microwave array, and also control some of the parameters to allow one wire, only one magnetic bit. Of course, there are some magnetic bits are not used and can be brought out to the channels. But that's okay because we based on the statistical methods to count the concentration of the biomarkers.
Okay, I understand. Okay. Do you need to wait for a long time to statistically evaluate the markers and these? You have to wait for a long time?
Actually, we have spent more than 3 years to develop these technologies. For the practical applications, most of the process time is spent on the preparation of the reagents and samples. During the process to use the microwave rate and the digital ELISA methods, actually the process time is quite short. So in our case, the whole process time is about 2 to 3 hours.
Okay. Any questions? I have one question. Could you show the slide number 9?
Sorry, sir.